You know how sometimes a news story just grabs your imagination. Suddenly you're just thinking about all the possibilities.
Oh, absolutely.
That's kind of where we are today, the James Webb Space Telescope. It's been focusing its, well, incredible gaze on this exoplanet, K2-18b,
Right.
and what it's seeing. Well, that's really got us wondering, hasn't it?
It really has. And, for folks who want to stay up to date with the really exciting discoveries, but maybe without getting totally bogged down in the super technical stuff.
Yeah, exactly. The aha moments.
Precisely. This deep dive is for you. Our goal today is basically to unpack these recent JWST observations of K2-18b,
Hmm.
which is a truly fascinating world.
Mm-hmm.
We'll be looking at what this new data tells us about its atmosphere, these um, intriguing hints of potential life,
Right, the big question.
and what it all means for, our ongoing search to figure out if we're alone out there. We're drawing straight from the latest JWST findings and the science analyzing them.
Okay, so K2-18b. People might have heard that name before, right?
Probably, yeah. It made a splash a few years back.
It popped onto our radar back in, 2019, when we first found evidence of water vapor in its atmosphere.
That's the one.
Now, just to set the scene, this isn't some Earth-like twin we're talking about here.
Not at all. It's quite different.
It's categorized as a sub-Neptune. So that means it's significantly larger than Earth, but smaller than Neptune.
Right. It fits into this planetary category that we actually don't have in our own solar system.
Which is fascinating in itself.
It really is. That's a key point. K2-18b, it's got about 2.6 times the radius of Earth
Okay.
and around 8.6 times the mass. Now, when you combine those measurements, something interesting kind of emerges.
Which is?
Its average density, it's surprisingly low, only about 2.7 grams per cubic centimeter.
Wow, okay. And Earth is?
Earth's is around 5.5, so
Yeah.
much denser.
Right.
This low density suggests that K2-18b isn't just a giant rock.
Yeah.
It likely has a substantial amount of lighter stuff.
Like gas or water.
Exactly. Gas or liquid water, making up a big chunk of its volume. It really occupies this intriguing sort of middle ground between the rocky planets we know
Like Earth and Mars.
and the much larger icy giants like Neptune out further in our solar system.
And it's orbiting a very different kind of star than our sun, isn't it?
It is. It circles a much cooler red dwarf star called K2-18.
But here's where it gets really interesting. It's located within that star's habitable zone.
The Goldilocks zone, as it's sometimes called.
Right. That's the region around a star where temperatures could potentially allow liquid water to exist on a planet's surface.
And in fact, K2-18b receives roughly the same amount of starlight as we do here on Earth.
Even from a dimmer star. That's surprising.
It is, yeah. Its estimated average temperature is even quite cool, actually, around -8 degrees Celsius. What's truly remarkable is that despite orbiting this red dwarf, which is, much dimmer and cooler than our sun, K2-18b still gets a similar level of what we call insolation, basically, the amount of starlight hitting it as Earth does.
Okay.
And considering its place in the habitable zone, plus that earlier discovery of water vapor by Hubble,
Right. The 2019 finding.
it became a leading candidate for what scientists are now calling a Hycean planet.
Okay, Hycean. That sounds, well, pretty sci-fi, right?
Yeah, it does a bit.
What does that actually mean?
So it's a newer term, yeah, a
Yeah.
relatively new idea. It's basically a mix of hydrogen and ocean.
Okay. Makes sense.
The concept is you've got this planet with a really thick atmosphere, mostly hydrogen,
Right.
and underneath that, a huge global ocean of liquid water. So imagine a world completely covered in water, but with a vastly different sky than ours, one mostly made of hydrogen gas.
Wow.
K2-18b fits the profile of a potential Hycean world, and this idea really expands our thinking about where life might, be able to take hold.
So life might not need conditions exactly like Earth to exist. It doesn't need our kind of atmosphere.
Exactly. That's the exciting part. Researchers have proposed that these Hycean worlds could actually be quite habitable, especially for microbial life.
Like extremophiles on Earth.
Precisely. We know that here on Earth we have extremophile microorganisms thriving in all sorts of seemingly nasty oceanic environments, deep-sea vents, super salty lakes, you name it. The vast oceans on a Hycean planet could potentially offer similar niches for life to evolve. Plus, from our perspective as astronomers,
Yeah.
these sub-Neptunes, with their large size and these puffy, hydrogen-rich atmospheres, they're actually easier to study than smaller Earth-sized planets.
Easier. How?
Well, that thick atmosphere gives us a stronger signal to analyze when the planet passes in front of its star. More atmosphere means more light interaction.
Okay, gotcha.
And like you said, the Hubble detection of water vapor was the first big clue that really supported this whole Hycean idea for K2-18b.
But it's not a totally straightforward picture, is it? I mean, there's still some big unknowns about this kind of planet.
Oh, absolutely. It's definitely not simple. We're still piecing together the likely internal structure of K2-18b.
Like what's underneath the ocean.
Exactly.
Yeah.
It might have a layer of high-pressure ice deep down, sort of like a smaller version of Neptune's mantle.
Huh. High pressure ice.
Yeah. And the atmosphere itself could have layers of clouds or hazes that would significantly affect how much starlight actually reaches the surface.
Affecting the climate.
Right, its overall climate. These complexities mean we can't just picture it as, a simple giant water balloon. It's more complicated.
Right. Okay. So how did JWST manage to get a better look then? What techniques did it use to peer through all that atmosphere?
So JWST used a technique called transit spectroscopy.
Okay, transit spectroscopy.
Imagine the planet passing directly in front of its star, from our point of view here.
Air transit, yeah.
As it does, some of the starlight has to travel through the planet's atmosphere before it reaches JWST's detectors. Now, here's the clever part. Different molecules in that atmosphere absorb very specific colors or wavelengths of that starlight.
Ah.
It's like each molecule leaves its own unique barcode or fingerprint in the light that passes through.
So by looking at the missing colors.
Exactly. By analyzing which colors are missing or dimmed, we can figure out which gases are present in the planet's atmosphere.
So like reading the atmosphere's fingerprint from the starlight. That's neat.
Precisely. For K2-18b, JWST primarily used its near-infrared imager and slitless spectrograph, or NIRIS,
Okay.
and its near-infrared spectrograph, in IRSpec. These instruments are really good at seeing light in the 1 to 5 micrometer range.
And why is that range important?
Well, it's crucial because many important molecules, like water and methane, has strong absorption features, strong fingerprints, in this part of the spectrum.
Got it.
And crucially, JWST also used its mid-infrared instrument, or MIRI.
MRI, okay.
MIRI extends our vision into the 6 to 12 micrometer range.
Mm.
This gives us a more complete picture, revealing different types of molecules potentially.
So multiple instruments, multiple wavelengths.
Exactly. The team observed multiple transits of K2-18b as well to collect enough light and build up a strong, clear signal.
Yeah.
You need that repetition.
And this detailed data revealed some really interesting stuff, didn't it? We saw the telltale signs of some key molecules.
We certainly did. The near-infrared data gave us clear, unmistakable detections of methane and carbon dioxide.
Okay, methane and CO2. Expected, maybe?
To some extent, yes, but the amounts are interesting. But what has really captured the scientific community's attention is the tantalizing evidence for dimethyl sulfide, or DMS,
DMS, okay.
and also the suggestion of dimethyl disulfide, or DMDS.
Right, I saw those mentioned. Sulfur compound.
Exactly. The initial near-infrared data hinted at DMS, and then the mid-infrared data from MRI provided independent support. It showed spectral features that seemed to be best explained by the presence of these sulfur-containing organic molecules.
DMS? That name sounds significant. Isn't that molecule strongly linked to, well, life as we know it?
You're absolutely right to pick up on that. On Earth, dimethyl sulfide is almost exclusively produced by living organisms.
Like what?
Primarily, those tiny marine plants called phytoplankton. They release it into the ocean, and it eventually gets into the atmosphere. It even plays a role in cloud formation and our planet's climate.
Wow, I didn't know that.
So yeah, the potential detection of DMS on K2-18b is incredibly exciting because it's considered a very strong potential biosignature.
A potential chemical clue that life might be present.
Exactly. Biosignature.
Wow. Okay, so let's really dig into what JWST found with these specific molecules then. What did the data tell us about each one?
Okay, let's break it down. Starting with the fundamentals, water vapor. It was detected again.
Consistent with Hubble.
Perfectly consistent, yeah. Which reinforces the idea of a world rich in water, very likely having a global ocean. Checks that box.
Good start for a Hycean world.
Definitely. Then we have methane, CH4. It was unambiguously detected. What's interesting there is that its abundance seems higher than what you'd maybe expect in just a pure hydrogen-rich atmosphere of a mini Neptune if there wasn't some active chemistry going on.
Chemistry potentially linked to that ocean.
Potentially, yes. That's
Wow.
one interpretation.
And carbon dioxide, CO2, is also clearly present, right?
Yes, carbon dioxide was definitively identified. No question there.
And why is seeing both methane and CO2 together significant?
Well, the fact that we're seeing both methane and carbon dioxide together is significant because it suggests an active carbon cycle and some ongoing atmospheric chemistry
Could be geology.
or biology.
It could be geological processes like gases being released from the planet's interior, outgassing, but it also doesn't rule out the possibility of biological processes playing a role. The co-detection of these two gases really lends support to the Hycean model for K2-18b.
Interesting. Okay, what about ammonia? I remember reading that its absence was notable. Why is that important? Exactly. That's a really interesting piece. One particularly intriguing finding from the JWST data is that ammonia, NH3, was not detected.
And we'd expect to see it otherwise.
In the hydrogen-rich atmosphere of a cold mini-Neptune, just based on pure chemistry, we might expect to find ammonia as a result of reactions between hydrogen and nitrogen.
Okay.
Its absence, especially alongside the observed abundance of methane and CO2, actually makes the Hycean scenario, the ocean world idea, more plausible.
How so?
The thinking is that if there is a global ocean, ammonia might be dissolving into it, or perhaps being chemically bound within the water, similar to what happens in Earth's oceans.
Ah, so the ocean is hiding the ammonia.
Potentially, yeah. So its absence isn't a contradiction, it's actually another intriguing piece of the puzzle fitting the Hycean picture.
Okay, fascinating. And now for the really captivating part, DMS, that dimethyl sulfide. What did JWST's observations reveal about that molecule?
Right, the headliner. The JWST data provide a tantalizing hint of the presence of DMS.
Just a hint, not definite.
It's not a slam dunk yet, no. As we discussed, on Earth, this sulfur-containing organic compound is almost exclusively produced by life.
Right, phytoplankton.
The specific patterns of light that JWST observed at certain wavelengths, around 3.5 to 4 micrometers, and again in the 6 to 10 micrometer MIR range, could be explained if there's at least around 10 parts per million of DMS in K2-18b's atmosphere.
Okay, 10 parts per million. How does that compare to Earth?
That's the kicker. To give you a sense of scale, the concentration of DMS in Earth's atmosphere is typically in the parts per billion range.
Billion, so 1,000 times less.
1,000 times less, yeah. So if this detection is confirmed, it would suggest a potentially very active biosphere on K2-18b, working on a scale maybe much larger than we see here.
20 times Earth's total biological DMS output, if I remember correctly. That's an astonishing amount.
That's the current estimate based on the signal strength, yeah. It sounds extreme when you compare it directly to Earth.
It really does.
But we need to keep in mind that K2-18b is a fundamentally different world. It could potentially have a much larger, maybe more productive, ocean ecosystem. Some recent modeling work has actually indicated that, yeah, a 20-fold increase in DMS production compared to Earth could be plausible for a thriving Hycean planet.
Yeah.
It's not completely out of the realm of possibility, theoretically.
Okay, wow. And you mentioned DMDS as well, dimethyl disulfide. That's another sulfur compound, right?
Yes, exactly. The mid-infrared data from MRI also provides some hints, maybe slightly weaker, but hints nonetheless, of the presence of dimethyl disulfide.
And that's related to DMS.
It is, yeah. DMDS is chemically related to DMS. On Earth, it's often found alongside it. It can be produced by certain types of microbes or just through the breakdown, the oxidation of DMS in the environment. The researchers analyzing the data found that the best fit to the MRI observations actually involves the presence of both DMS and DMDS.
So seeing both together,
Yeah.
that strengthens the case.
It potentially does, yeah. The fact that we might be seeing both of these sulfur-based molecules, which are so closely linked to biological activity here on Earth, really amplifies the excitement around these findings.
So DMS being a biosignature, what makes it such a compelling indicator of life compared to, say, methane or oxygen?
That's a great question. It really comes down to its strong and almost exclusive link to biology on our planet, on modern Earth anyway.
The 90% from phytoplankton number.
Exactly. About 90% of the DMS in Earth's atmosphere originates from marine phytoplankton. There just aren't any significant non-biological or abiotic processes that we know of on modern Earth that produce it in comparable amounts.
Okay.
Therefore, finding it on another planet, especially in these potentially high concentrations, would be a very, very strong piece of evidence suggesting the presence of life.
And it's a different kind of clue than the ones we usually focus on, like finding oxygen in a planet's atmosphere.
Precisely. DMS would represent an independent biosignature. We often talk about oxygen or maybe methane in certain contexts in Earth-like atmospheres
Hmm.
as potential indicators of life.
Right.
But while methane, for instance, can be produced by living organisms, it also has several well-understood abiotic sources, non-biological sources,
Like volcanoes.
like volcanic
Right.
activity, yeah, or certain geological reactions.
Mhm.
DMS, particularly in the context of a Hycean world like K2-18b with its hydrogen-rich atmosphere, seems potentially much more specifically tied to biological activity based on our current understanding.
Makes sense.
And as we said, the possible co-detection of DMDS potentially further strengthens this
Yeah.
biological interpretation because they often go hand in hand biologically here.
This is all incredibly exciting to think about, but I know in science we always need to approach these things with uh, a healthy dose of caution.
Absolutely essential, critical.
What are some of the reasons for scientific skepticism regarding these findings? Why isn't everyone shouting aliens yet?
Well, exactly. While these initial findings are incredibly tantalizing, it's crucial to remember that attended detection is not definitive proof of life, not even close yet.
Okay.
For one thing, the signals for DMS, and maybe DMDS, in the current data have a statistical significance of around 3 sigma.
3 sigma. What does that mean in plain terms?
In simple terms, it means there's still a small chance, about 0.3% or 1 in 300 roughly, that these signals could just be due to random noise in the data or maybe some other unknown factor we haven't accounted for.
Okay, so not impossible, it's just a fluke.
Not impossible, no. In the scientific community, especially for something as profound as finding life, we generally look for a much higher level of confidence, typically 5 sigma.
Which is much, much less likely to be a fluke.
Much less likely, yes,
Yeah.
like a 1 in 3.5 million chance. So the team behind these observations, they're well aware of this. They're planning further observations with JWST specifically to try and increase that level of certainty to see if the signal holds up and gets stronger.
Okay, so statistical uncertainty is one reason for caution. What else?
Well, there's also the possibility that other molecules present in K2-18p's atmosphere could be sort of mimicking the signal of DMS or DMDS, right?
Like spectral overlap, things looking similar at this resolution.
Exactly. When we analyze these spectral fingerprints, it's possible that other molecules in the atmosphere could have absorption features at similar wavelengths to DMS or DMDS, especially with the current level of detail we have from the data.
Any specific culprits?
For example, some scientists have suggested that certain types of hydrocarbons might potentially produce similar spectral patterns under the right conditions. The researchers have explored some of these plausible alternative molecules in their analysis, and they don't seem to fit as well as DMS-DMDS.
Okay.
But obtaining higher resolution data, cleaner data, will be absolutely essential to definitively rule them out. And also, as we touched on earlier, current data doesn't really allow us to completely distinguish between DMS and DMDS. The observed features could be a combination of both, or maybe predominantly one over the other. We need more clarity there, too.
Got it. And what about non-biological ways to produce DMS or DMDS? Could there be natural geological or, I don't know, chemical processes on K2-18b that could create these molecules without life being involved at all?
This is a critical question, probably the critical question, besides confirming the detection, and scientists are actively investigating it.
Because K2-18b isn't Earth.
Exactly.
Hmm.
While DMS doesn't have significant non-biological sources on Earth today, K2-18d is a vastly different environment. We have hydrogen atmosphere, different star, different size.
Right.
Some research has explored whether photochemical reactions driven by the red dwarf star's ultraviolet radiation involving other sulfur-containing gases could potentially lead to the formation of DMS without needing life.
And it could they?
Studies have shown that this might be possible under certain, sometimes pretty extreme conditions. Whether those conditions apply to K2-18b is still an open question. There's also the hypothetical possibility of volcanic activity releasing precursor molecules from the planet's interior. They could then react in the atmosphere to form DMS or DMDS. Again, this isn't a confirmed process for K2-18b, just a possibility we need to consider. So it's vital that we carefully consider and try to rule out all plausible non-biological explanations for these potential detections before jumping to conclusions.
That makes sense. And the fact that K2-18b itself is just so different from Earth, its size, gravity, atmosphere, that must also play a huge role in how we interpret these findings, surely.
Absolutely. You can't just transpose Earth-based assumptions directly. K2-18b's larger size means it has stronger gravity,
Right.
which in turn likely leads to a much denser atmosphere with much higher pressures than we experience on Earth, especially deeper down.
So the conditions near this potential ocean could be extreme.
Very extreme.
Oh.
Current models suggest that while the upper atmosphere might be relatively temperate, deeper down, the pressure and temperature could be so intense the ocean might be very hot, or even exist in a state called supercritical water.
Supercritical water.
Yeah, it's kind of like a weird fluid state that's not quite liquid, not quite gas. Very different properties than the water we're familiar with. Whether life as we know it could exist there is a big question mark.
Mm.
Some scientists have even suggested that the strong greenhouse effect created by such a thick hydrogen atmosphere could make the surface temperature far too hot for Earth-like life to survive, regardless of the water state. We need to consider that possibility too.
And the star itself. Red dwarfs can be problematic, right?
They can be, yes.
Yeah.
We also need to remember K2-18b orbits a red dwarf star. These stars are known to be more magnetically active than Sun-like stars. They're prone to powerful flares, emitting higher levels of X-rays and ultraviolet radiation.
Which could be bad for life.
It could certainly pose challenges for life on or near the surface, yeah.
Mm-hmm.
And look, we've also had experiences in the past, historically, where initial exciting claims of biosignatures on other planets, like phosphine on Venus recently, or even earlier, less certain reports about K2-18b's water. They were later revised or explained by non-biological phenomena as we got better data or did more analysis.
Right. The phosphine story is a good example of that caution.
Exactly. So maintaining a healthy level of scientific skepticism and demanding rigorous evidence is always essential in this field.
Okay. So while this is undeniably exciting, really exciting, we're still very much in the early stages of trying to understand the true implications of these JWST observations.
That's precisely right. Think of it this way. These initial observations are a really significant leap forward. It's the first time we've potentially detected multiple molecules that could be linked to life in the atmosphere of a habitable zone exoplanet. That's huge.
It is.
But it's really just the beginning of a much more in-depth investigation. It's not the final answer by any means. We can anticipate more data coming from JWST in the future.
Specifically looking for DMS again.
Yes, specifically designed to improve the clarity, the signal-to-noise for DMS and DMBS, and also to search for other potential biosignatures that might be present to build a more complete picture.
And looking beyond JWST, thinking further ahead, what's on the horizon for the search for life on these kinds of planets? Are there even better tools coming?
Oh, yes. The next generation of telescopes promises to be transformative. For instance, NASA is planning the Habitable World Observatory, HWO.
Okay.
That mission is being designed specifically to directly image and analyze the atmospheres of Earth-sized exoplanets orbiting Sun-like stars. That's a whole different ballgame.
Wow. Direct imaging.
And the giant ground-based telescopes currently under construction, like the Extremely Large Telescope, the ELT, in Chile,
Right.
they'll have incredible light-gathering capabilities. That will allow us to study the atmospheres of more distant or smaller exoplanets in unprecedented detail. These future instruments, combined with ongoing advancements in our data analysis techniques, they'll be crucial for confirming potential biosignatures like DMS, if they are truly there.
And understanding the planets themselves better.
And for gaining a much better understanding of the diverse range of planetary environments where life might actually be able to arise. As the researchers themselves have emphasized, K2-18b really highlights the importance of expanding our search for life beyond just planets that look like a slightly different version of Earth. We need to think broader.
Think outside the Earth box, so to speak.
Exactly.
So, to bring it all together then, what's the key takeaway from this deep dive into the new observations of K2-18b, if someone remembers one thing?
I'd say the main point to remember is that JWST has provided us with really intriguing, tantalizing evidence for potential biosignatures, specifically DMS and possibly DMDS, in the atmosphere of K2-18b. And this planet is a Hycean candidate world, located within its star's habitable zone.
It's a significant step forward in the
A very significant step forward in our quest to determine if life exists beyond Earth, absolutely.
And it's a big but, even with all the excitement surrounding the possibility of life, we have to maintain that scientific perspective, right? Further investigation is definitely needed to confirm these initial findings.
Absolutely critical. While the prospect of life on K2-18b is incredibly exciting, and it really captures our imagination,
It does.
it's vital to remember that this is still tentative. It's potential. More observations are necessary, higher quality data is needed to confirm these initial detections, and, just as importantly, to rigorously explore and rule out any plausible non-biological explanations for the presence of these molecules.
Well, this has certainly given us a lot to think about. The idea that life might exist in such a fundamentally different environment than our own, it really makes you wonder about all the possibilities out there, doesn't it? Thanks for taking this deep dive with me today.
My pleasure. It's fascinating stuff. And for everyone listening, maybe consider this. Our ongoing exploration of K2-18b isn't just about one far-off world. It represents a crucial step in addressing one of the most fundamental questions we can ask. Are we alone in the cosmos?
The big one.
And perhaps even more fascinating to ponder is, how soon might we actually find definitive proof of alien life? Especially if it turns out it can thrive in environments so wildly different from our own. It's a truly mind-expanding idea to mull over.